All right, pre-calculus chapter 4 closure. All right, number 127, we want to represent this using sigma notation. So when I look at this, I notice there's a 0.5 as part of all of the terms. So I'm going to have a 0.5 here. And then when I look at this number here, I've got like a 2 and then a 2.5 and a 3, and it goes up to 12. So this is, there's more than one way to do this, but if we kind of take it back to when we were doing area under a curve, this is like at x sub 0, at x sub 1, at x sub 2, and it's so on. At x sub we don't know yet. Okay, but I'm starting at 2 and I'm going up a half every time. Right, so if I was thinking this almost as like that idea of an x sub k, is that I'm going up by 2 by half every time, so 0.5k, and then if I'm going to start at 0, then this is plus 2. And that expression is always under a square root. So this would be the square root of 0.5k plus 2. Now that's if I start with k equal to 0. And so then we're like, all right, well, what do I have to plug in here for k? Because I have to figure out what goes at the top. What would have to go in for k to give me 12 as an answer? So you could keep going, all right, I'm going to keep adding 0.5, 0.5 all the way up to 12. Or I want to know 0.5k plus 2, if I had that equal to, what would make k value make this equal 12? And you could just solve that quick equation. So I could subtract 2 and get 10. And then if I divide by 10 by a half, I would get that k is 20. So the last number that I would have to substitute in to make this last value under the radical of 12 would be a 20, right? Half of 20 is 10 plus 2 is 12. All right, so the last number I would plug in is 20. So then this would be my sigma notation. You also could have had this 0.5 out front. That would work also. All right, 128 asks us to sketch this function here and then approximate the area of this function from 5 to 8 using both 6 endpoint, right endpoint, and 6 left endpoint rectangles. Excuse me, and then write both of the sums using sigma notation. Okay, so when I think about what this would look like, I know a square root function, the parent function would be something like this, and this minus 3 is moving it to the right 3, and then the plus 4 is moving it up 4. So if I'm just thinking about like a sketch, instead of going to the right 3, then I'm going up 1, 2, 3, 4, like this, and then it's kind of going something like this. But I want it from 5. Let me pause this. All right, I'm sure you can tell that I'm trying to do this right at the end of 4th hour. All right, but we want to do this from 5 to 8. So 1, 2, 3, 4, here's 5, right, to 8. It says 6 endpoint intervals. So from 5 to 8, I want 6 rectangles. And we could draw in the rectangle. So I see there's 1, 2, 3 spaces. So I'd have to have half like each. So from 5, and then 1, 2, 3, 4, 5, 6 to 8. So from 5 to 8 is a difference of 3. So this would be like 5.5, 6, 6.5, 7, 7.5. Okay, we could draw all these little rectangles and they want the left endpoints. So that would be like on this side and the right endpoints. We don't really, I don't think we really need the graph to answer this question though. And so from 5 to 8, and then like I want to write a rule for my x sub k. All right, this would be 2, 3, 4, 5, 6, x sub 6. I see I'm going up by half every time. So my x sub k would be 0.5 k plus I'm starting at 5 when the subscript is 0. So when we do a left endpoint, the rule is that you start at 0 and you go up. If this is the 6th, right, I want to go, the last left endpoint is here. So I go however many rectangles minus 1. And then delta x, which is like the width of my interval, and then times f of x sub k. That's how I get my sigma notation. Okay, for a right endpoint, it's the same rule, except for now, if I want to start with my right endpoint, I would be starting with 1, and I would end with my last one, which would be 6. Okay, so it would be that we start with 1, And then we end with whatever our K value was, which in this case is 6. So I'm going to put a K there for in general. So if I'm writing this rule, this would be K equals 0 to start. And then the number of rectangles take away 1. So this would be 5. My width is 0.5. And then f of x sub k. So in this rule here, my rule for x sub k is this. In this rule, in place of the x, I'm going to put in this. So I would have times 4 plus the square root of 0.5k plus 5. And that would be for my left endpoint. For my right endpoint, this would be the k equals 1 on the bottom to 6. 0.5 is still my width. And sometimes the book will put the answer on the outside. It really makes no difference. I mean, this all stays the same. Whoops, this should be a 4. Okay, so this should be 4 plus the square root of 0.5k plus 5. Okay, and then if we wanted to find the sums, then we could just put these into decimals or into our graphing calculator. So, and use the notation. So this is 17.36 square units. This is 17.771 units squared, right? So this is an underestimate, this is an overestimate. All right, 129 says graph this. Okay, so we're going to just start with a sketch, and then it says state the locations of the intercepts, and then use a graphing calculator to check your answer, locate the extrema, and then the intervals when it's increasing in the concavity. Okay, so when I look at this, first of all, when I want to find the intercepts, I notice that these are not in factored form. So this, I'm going to factor. This would be difference of squares. So x plus 1, x minus 1. And this would be, if I factor this, it would be x plus 4 times x minus 3. You can use a box to factor that. So I'm going to have 1, 2, 3, 4, 5 intercepts. Whatever makes this equal 0 will be an intercept. So I'll have an intercept at 0, at 1, it's supposed to be a 1, it doesn't look like a 1, at 1, at -1, at -4, and at 3. Okay, so I'm going to have 5 intercepts, and these are all first degree, so it's just going to go through them all, right? I've got 5 of them. This has a degree of 5, which means it's going to be up on the right and down on the left, and it's going to hit our intercepts in between. So it's going to have our wiggles in between. All right, here's what it ends up looking like here. Right, so I've got the 1, 2, 3, 4, 5 intercepts. And it's going through them all. Extrema are here where I have these turning points. It goes up and down forever, so it has no global max or min, but here we would say this is a local max at, and I'm just going to write it here, this is a local max here. This right down here, it has no min. This right here would be a local minimum. This up here would be a local maximum. And then this down here would be a local minimum. Those are our extrema. And then the intervals where the function is increasing. So as you look from left to right, it's increasing here. So we want to state the x values for which that's true. It's increasing here. And it's increasing here. So it's for what x values is it increasing? So this starts increasing at this x value here, which is this -3.115, and it's everything back here, it's increasing. So I could say x is less than -3.155. Okay, not equal to, because at that value of -3.115, it's not increasing or decreasing, it's a maximum. You could also write it like this. It's also increasing here from here to here. So at this x value, which is this -0.576, to this x value, so in between here, which is this 0.556. So we could say -0.576 is less than x is less than 0.556, which you could also write like this. And then again, it picks up increasing here at this x value of 2.375, and it's increasing forevermore. So you could say x is greater than 2.375, or you could say 2.375 to infinity. All right, and then when it says to One second. Sorry, interrupted again. Okay, and then when it says describe the concavity, so concave up, right? This is concave up, concave down, and we're kind of I'll be kind of accepting of your different intervals. Like you could say it's concave down, like I would say this little section here is concave down. So maybe from here to like, I don't know, here. So from this value to this, you could even say maybe from, what was this at? Negative, is that at 4? -4 to -1 maybe. You could say it's concave down, and then here maybe from -1 to 0, it's concave up. And then from 0 to 1, it's concave down again. And then from 1 and beyond, you could say maybe x is greater than 1, or if you want to say from 1 to whatever that is 3, you could say concave up. All right, 130, write a possible equation for a polynomial function in factor form with integer coefficients that has these roots. So x equals 1 plus I, and then x equals the square root of 3. Okay, so there is, and the and has a double root at x equals -4. So this is easy because if it's a double root, it bounces at -4. So if the root is at -4, right, I could turn it into a factor by adding 4, and I could say x plus 4 is the factor, but because it's a double root, the double root means that this is squared. Okay. Now for these, I could set the factor up. I could do x minus this whole thing, and I could do the same thing here. Another way to do it though is to kind of use the same idea that we did here and write the solution. So if the solution is x equals 1 plus I, what I'm going to do is I'm going to subtract this 1, and x minus 1 equals I. And then I want to get the factor. I'm going to square this. So I squared I know is -1. And I'm going to expand this like using a box. So x squared minus 2x plus 1. And then I'm going to add this 1 over. So x squared minus 2x plus 2. Okay, so this is another factor right here. Now, if the other option, first of all, because this is a solution, so is its conjugate, you could write the factors as x minus 1 minus I, and then x minus 1 plus I, but then you would have to like multiply this out, then you'd have to make a box and multiply out that 3 by 3, which is a lot. This to me is faster. Okay, I could use the same idea here. If x equals √3 is a solution, I could turn it into a factor. I'm going to square both sides, so I have x squared equals 3. And so then I would have x minus 3 equals 0. X squared minus 3 equals 0, right? We don't want that, right? Usually we have integers for our like factors, right? We don't usually have those radicals. So then I get this. And again, if √3 is a solution, so is its conjugate, -√3. So you'd have to think of that if you want to do x. You could do x minus √3 as a factor, but then you would also have to have an x minus a -√3 as a factor, and you'd have to multiply that all out. So what's easier is to kind of think of it as going backwards to the solution, from the solution to the factor. So here's a factor, here's a factor, here's a factor. So then our polynomial would be f of x equals this times this times this. So x plus 4 squared times x squared minus 2x plus 2 times x squared minus 3. Right? And the order you have these factors in does not matter. Right? So that would be fine either way. All right, so 131 we want to solve. So first, I think for 131, I would add this 45x to both sides. So I'd have x to the 4th plus 5x cubed plus 9x squared plus 45x equals 0. And I do notice that like here, these both have a 5 in them, like a 9 in them rather. So what I notice here is I could pull an x cubed out here. This would be x plus 5. And then here I could pull a 9x out. This would be x plus 5. And then it's like I have an x plus 5 as a common factor. And I'm left with x cubed plus 9x. And then, and I'm trying to solve this, right? And then I could pull an x out of both of these. So I have x plus 5 times, I could pull an x out of each of these. And then have x squared plus 9 equals 0. And now that it's factored, I can set my factors equal to 0. So x plus 5, well, this just gives me x equals negative 5. This would just be x equals 0. And then, I don't do this. Then I'm also going to need to solve this x squared plus 9 equals 0. So x squared equals negative 9. And when I take the square root of both sides, x equals positive or negative. You can think of that as negative 1 times 9 or I squared times 9. And the square root of I squared is I, and the square root of 9 is 3. So this gives me x equals plus or minus 3i as a solution. You could also have solved this. I guess you could solve it differently. Maybe you notice there's an x as part of all of them. So you could have pulled an x out as a greatest common factor first. And then this gives you the solution x equals 0. And then you could have factored this. You could have put it into a box also. And just put, there are 4 terms already. So just put all 4 terms into the box. And here I could pull out an x squared and have an x. And then here I would have plus 5. And here I would have plus 9. So I get this x plus 5, which is right here. And I get this x squared. I already pulled the x out of this here. And then I had this x from down here. And then you could solve it that way. That's another way to go. All right, so for this one, I would get everything onto one side. Whenever you're solving a polynomial, you want everything on one side. So I'm going to subtract out the x squared and the 1x here. And then we could go for a box here. It's already 4 terms. So I'm just going to put everything into the box. Here I could pull out an x squared, and this would be an x and a minus 1. And this would be a minus 1, right? And that works. And so then I have x minus 1 times x squared minus 1 equals 0. The x squared minus 1 factors into x minus 1 times x plus 1. So I get x equals 1, that's a double solution, and x equals negative 1. Well, it doesn't look like it says negative 1, but that's what it's supposed to say. X equals negative 1. So those would be your solutions. All right, so 132, it says without using a calculator, sketch the graph of this. First, rewrite it as a transformation of y equals 1 over x and state the locations of the asymptotes. For this one, I think what I might do is I might just divide, right? Just set up a division. And I'm going to put the negative 3x here. So this would be negative 3, and then this would be 6. And then I need these constants to add up to be 7. So I have to put a 1 there. So this I can rewrite as negative 3 plus my remainder over my divisor. So when we write it as a transformation of this, though, we usually would write it as, we write this like at the end, that's like our k value. So 1 over x minus 2 minus 3. So when I look at this and it's a transformation of this, I know that this minus 2 tells me I've gone to the right 2, and this minus 3 tells me I've gone down 3. So normally this graph, the asymptotes are the x and the y axis. Now I'm going to the right 2. So now I'm going to have a vertical asymptote through 2. And I'm going down 3. So now my horizontal asymptote is down 3. And so as I was talking about that transformation, I was already stating my asymptotes, right? So if I went to the right 2, I have a vertical asymptote at x equals 2. It's a line, so it has to have an equation with a variable, x equals 2. And I went down 3. So that's my horizontal asymptote, y equals negative 3. So I went down 3. Okay, and then, I mean, if it's a sketch, really, you could just sketch your branches in. It's most important to know kind of what quadrants they would end up in, but that would be fine right there. All right, so now 133. This is fun, right? So we're given f of x, and then we want to sketch all of these transformations. Okay, and so for each of these transformations, we want to, I'm just going to sketch them on the same graph. I think that will be easiest. All right, so the first one is 2 times f of x. That means all of my y values have to double. Okay, so all of my y values have to double. So this one, the y value right now is at 2. The y value has to double, and now my y value needs to be at 4. Okay, so the x value is going to stay the same, as that my y value here is going to be at 4. Okay, for that, and then I would just do that with, you know, a few of the kind of key turning points. So like this one, instead of being at 2, the y value is going to be at 4. But if I pick this point, the y value is at 0. So the y value is just going to stay at 0. And this y value is just going to stay at 0. So then I can draw this through. You can just see it's been vertically stretched, which is what we should expect when we've got that 2 on the outside. This should actually go through that point, but it's hard to do it with this pen. All right, now this one, the 2 is inside. So we should expect a horizontal compression, right? If it's on the outside. So it should be getting, the x is getting smaller, compressed by half. So this is the x is compressed by half. So for each of these, for each x value, I want it to be half. Okay, so if this x value for this one is at -2, now I want my x value to be at 1. So it's going to be here. And this x value, instead of being at 2, is going to be at 1. So you can see it's been squinched in, right? And this x value is at -3. So now it's going to be at -1.5. And then same, this was at 4. Now the x value is going to be at 2. Okay, so then you can see it's been messily compressed. Okay, the next one is f of x is -x, the opposite of x. Okay, so all the x's are going to become opposites, right? So x's are going to be the opposites. Basically, remember, if you remember this from before, this means a reflection over, instead of the x-axis, if the negative's out here, it's a reflection over the x-axis. This is going to be a reflection over the y-axis. So really, I could just think of it that way. All of the x values are going to be flipped. So this one's going to come over here. This one's going to come over here. This one's at what, -3. So it's going to come here to +3. This one's at 4. It's going to come to -4. So it's just going to be flipped over. Okay. And the last one, I think I'm going to have to rewrite it. There's no way I'm keeping this all in my head at the same time. So opposite of f of x plus 2 minus 1. Okay, so that negative in front is going to reflect, right? That's going to reflect over the x-axis. This is going to move it to the left 2, and this is going to go down 1. So each of these points is going to have to flip over, and it's going to have to shift. Okay, so I think I'm just going to take this. When this flips, it stays where it's at, but then it's got to go to the left 2. So 1, 2, and it's got to go down 1. So right here, this point goes to here. This is going to flip over. That's going to bring it here. It's going to go to the left 2, and it's going to go down 1. I'm going to go to this. This one is going to flip over. It's going to go to the left 2, right, left 2, down 1. So I can sort of see it coming together. Right? This will be here, here. All right, and then this one's going to left 2. Well, it's going to flip over, so it stays to the left 2, down 1. So right there. All right. This one, graph at least 2 complete cycles of each of the trigonometric functions. Okay, so here, this 4 is my amplitude, is 4. Okay, this period is 2 pi over b, so 2 pi over 6, which is pi over 3, block. And then this is a vertical shift of down 4. Okay, so if I go, so we always start with going down 4, that's our new midline. And I think I can fit this with a scale of 1. So I'm going down 4, that's my new midline. Okay, I got an amplitude of 4. So from my midline, I've got to go up 4 and I've got to go down 4. So now I know I'm contained within there. It's a cosine. Parent function for cosine goes like this. Right, I've got these 5 key points. And my period is, what do we say? Pi over 3. I'm going to set my scale up here to jive with my scale I have over here. Okay, so if that's pi over 3, half of pi over 3 is pi over 6. So I think I might say, I got to get 2, I might just say, here's pi over 6, here's pi over 3. Okay, that's 1 pi over 6, 2 pi over 6, 3 pi over 6, this would be half pi. It's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6 would be 2 pi over 3. All right, so 2 cycles. So when I go to graph this now, I know I start at my maximum. So here's my maximum. Halfway, so right here, halfway between 0 and pi over 6, I hit my midline. So here's halfway, I hit my midline. Pi over 6, I hit my minimum. And then halfway between here and pi over 3, I hit my midline again. So right here, and then at pi over 3, I hit my max. Okay, and then I'm just going to continue the fun until I get another cycle. And then it's going to look really wonky because using this pen is not really easy to do, but it should be curvy, not VE. It should actually go through the points. It should not extend past where you put your boundary lines. All right, next one, a tangent. Okay, tangents. Tangents, the period of a tangent is pi. So when I go to find my period, it's pi over b, not 2 pi over b. So my period is pi over 2 instead of pi. And it's shifting down 5. So it shifts down 5. So 1, that's here, right? That's my new midline. Okay, so here's the thing with a tangent. A tangent normally would have a period of pi, and this would be at pi over 2 right here, and this would be at negative pi over 2, because it would usually be a distance of pi. But now the period is half pi. So this distance has to be a half pi. So instead of this being pi over 2 and negative pi over 2, it's going to be pi over 4s. Okay, and then it usually hits in the middle and then has almost like a cubic shape to it. So I want to have my, I can say like this right here is pi over 4, and let's say this is negative pi over 4. And those are where my asymptotes are. And then this would be a half pi, and then this would be like 3 pi over 4. I would have another. I need at least 2 cycles. I need to have at least 2 full branches. And then I just have to make sure when I draw my branches, they have to hit at my new midline, right halfway between where my asymptotes are. So it looks something like, whoops, it should go through that point, sorry. And this should go through that point also. That's a little bit better. And then this is our last one, yes. Use polynomial division to describe the shape of this graph. Okay, so first let's do this division. So x minus 2, and this is 3x squared, and this would be 3x, and this would be negative 6x. I have to have my x's add to be negative 2x, which is going to make this 4x, and plus 4, and negative 8, and then I have to have my ones add up to, or yeah, my constants add up to b1, so this has to be 9. Okay, so this is equivalent to 3x plus 4, and then plus 9 over x minus 2. All right, so we want to describe the shape of this graph. All right, well, the shape of this graph, as x gets really, really big, as we put in bigger and bigger values for x, the overall value of this is going to be 0. Right? The limit of this is going to be 0. As x gets bigger and bigger, it's going to be 0. So remember we talked about as you put in bigger and bigger x values, it describes the end behavior of what's going to happen. So what's going to happen is overall, the graph of this is going to look like the line y equals 3x plus 4. So 1, 2, 3, 4. Let's see, here's 4 and a slope of 3 over 1. So overall, my graph is going to look like this. But it's going to end up that we have like this, kind of like a hole at 2. See, could we also have factored this? Let's see, does that factor? I put a negative 1 here. No, it doesn't end up factoring. But what ends up happening is the end behavior is going to head towards this 3x plus 4. Okay. All right, so I hope that helped with the closure.